No, I did not get that.
Yeah, those are off-camera conversations that we have.
Behind the scenes.
Don't make YouTube. Yeah, that ends up on the floor.
Fake it behind
That's how
the
we get
scenes.
the
Okay,
monetized.
so here's
Behind the scenes blog.
the second to the last big type of energy that we need, and this is energy stored in the spring. So we have KT, which is 1/2 mv squared. We have UG, which is mgh. And all of these, in terms of units, work out to be kilograms meter squared over second squared, which is also known as Newton meters, which is also known as joules. Okay? Now, so when I look at this spring, so springs are cool, one of our better inventions. So if I pull this down, first off, do I do work?
Sure.
Why?
Because you're exerting a force.
And if you let
over
go,
a
something would
distance.
happen.
Yeah. Okay, number one, I exert a force over a distance. And if I let go of it, something happens, right? And it's the same thing true of this spring for the marble launcher. Okay? So I've got it here. I pull it down to, say, that third notch. I just did a certain amount of work because I exerted the force over the distance. I flip it, and
The ball
that
goes.
could not have gone worse. So that potential energy that you stored turns into kinetic energy, the ball goes up, potential energy changes into, or the kinetic energy changes into potential energy. We're good, don't worry about it. Now, so if you're looking at a spring, so let's say that you've got this. So I've got a spring, I exert a 20 Newton force, and I measure the elongation. Remember this, remember this, remember this, remember this, remember this when you're dealing with springs. It is not the length of the spring. It is how far the spring stretches from its equilibrium point. And the same thing is going to be true if I compress that spring. How far did I compress that spring from the equilibrium point? So I hook this up, I measure, hey, here's a 20 Newton force, probably about 2 kilograms, and it stretches 20 centimeters, which would be about like yay. So when you're dealing with springs, and this, you have to graph it in this way or the units don't work out. So you're going to put force on the y-axis and elongation on the x-axis. Now, here's the other thing that's unique about springs. Because it follows Hooke's law, you cannot, listen to me, you cannot draw it as a horizontal line. This is not, hey, I'm going to pull the block and I'm going to apply the same amount of force over this distance. So when you draw graphs with springs, and you're graphing force and elongation, it is not a horizontal line. Now, here's the story. At this point, would you have enough information to calculate the slope of the line?
No.
If you have,
Yes.
If you have elongation and force, then yes.
What would the slope of the line be?
Like 100? No. 20 divided by 0.2.
So,
No, you're right.
Oh, 100, yeah.
slope of the line is going to be 20 newtons
I was like,
minus 0 newtons over 0.2 meters minus 0, and you're going to get what? 100?
yeah.
Put the line over the top, says, hey, these are significant values. Now, Colin,
1E.
what units is that in?
The units are in, of the slope,
Yes.
are in Newton over meters.
Yeah. Now, this is not Newton meters, okay?
It's per meter.
It is not Newton meters.
Evil
Nuh-uh.
Evil Newton meters.
It is newtons per meter. So what this says is that for every meter of elongation that you want, this is how much force it's going to take. So since it's Newton per meter, this is not joules. Don't look at this and go, oh, that's Newton meters, it's joules. No,
Yes.
it's not.
I would
Now-
make it so.
This slope is what we call lowercase k.
Inverse joules.
This is what's known as the spring constant. Okay? This is not the same for every spring. Okay? It varies greatly depending upon the ability to compress or expand the spring. If it's a really lightweight spring, hey, this number isn't going to be very big. If it's a big massive spring, hey, that's going to be a really big number to compress it or stretch it 1 meter. So this is not the same. This is not like the universal gravitational constant that says, oh, it's always the same number. No, this varies greatly depending upon the spring. So here's what we've got. This is very much a linear function where you have y equals mx. So I'm going to do a little bit of hocus pocus, and I'm going to say that equals f, which is what's graphed on the y-axis. And then you have your slope, which we just said was the spring constant. Okay, cool. And then I've got my change in x, my elongation. Now, clearly, if I don't apply a force, what's going to be the value of my change in x?
0.
Zero. Mother Nature is a lazy prima donna. If I don't apply a force to this spring, it's not going to stretch. But the more force that I apply,
It's pouring in.
the farther it stretches. Okay? So because this is a linear function, this is why you cannot draw this as a horizontal line when you do forces with springs. Okay? Now, here's the story. Could I, Cohen, find the area underneath that line?
Sure.
What would that be? Just general idea. It's
In
trying.
Newton meters.
Beyond, no, don't, we'll get to that. Area of
For-
triangle,
Oh, the triangle? Well, base is whatever, 0.2. Height is 20, so 0.2 times 10, 2.
It's 50.
1/2 base times height,
Yeah.
right? So the area, we'll get to that,
Is 50.
Yeah.
is gonna be 1/2, let's just look at the units. So the base is gonna be in
Meters.
some number of meters, and the height is gonna be in,
Newton.
so you get Newton meters, which represents
Energy.
Joules.
energy or joules or work. Okay? Right? So in this situation, I had 0.2 meters and I had 20 newtons, so that's
2 joules.
2. So by stretching that spring 0.2 meters, I did 2 things. I did 2 joules of work, which is also the amount of energy that I stored in the spring. Okay? Did 2 things. Stored energy, did work. Now, we're going to do a little bit of hocus pocus. Okay? So, this area is 1/2 force times
Multiply by 2.
delta x, right? That's how we can do it. It's the force
Yes.
and delta x, true?
Yep. Whatever you said.
Now,
was.
we just said force equals k delta x. So can I put that into here?
Yeah.
Yeah.
Is it gonna be delta x squared?
Oh, k times delta x
Squared.
squared. Now,
Wowzers.
let's see if the units work.
Is that an equation? I mean, yeah.
No, I just made that.
I don't think that we know.
So,
Not equal.
I've got my k value, which is going to be in
Newton meters. Dang it.
Newtons per meter.
newtons per meter.
The evil twin.
Yeah.
X is going to be in
Meters.
Squared.
You can say what x squared is gonna be, and
I'm gonna cancel out one of the meters, and I'm gonna get
Newton meters.
otherwise known as
Energy or work.
joules of work. Okay? Now, so the area underneath here is gonna represent one of two things. It's either gonna represent the work, or it's gonna represent
The joule.
the energy that was stored. Now, for those of you that are math nerds, okay, which is about everybody in this room, God bless us all. This is a linear function, right?
Calculus.
So let's do a little calculus.
Yay!
Kx dx,
Derive it.
right?
I haven't taken
Over the interval from 0 to
Oh, you pulled the-
0.2.
Oh,
Don't know what this means.
so well,
No.
And dx, remember, anytime you see dx, that just says we're gonna break it up into tiny, tiny little bits of x. Anytime you see dx, means tiny little bits.
Is that just a definite integral?
So,
yeah. Wait.
How
Are
do
we
you take-
integrating or are we deriving?
Integrating. That's
We're integrating.
Okay. Yeah.
so we raise the exponent up to a power of,
Three.
Three.
it's x.
To raise it one.
One. One.
1/2 kx squared? Have they not taught you this?
Well, no, they
No,
have.
I've not been taught this yet.
Okay?
You just write it different.
Why do you write it
No, I
differently?
mean your handwriting's different, so it's a struggle, okay?
Colin is blind.
Blind and illiterate.
This is physics handwriting, not calc handwriting.
And you put in the value of 0.2, oddly enough, you're going to get the area underneath the line. So if you're a calculus nerd, when you have a force x wrath, no matter what it is, when you find the area, you find the work, which is the change in the energy.
Maybe next.
Okay.
Next semester I'll be a physics.
Now,
Calculus.
let's see how this plays out. So, let's say that I have this cart, okay? And y'all dealt with this cart before, we did a lab with it, remember?
Oh,
Came
yeah.
in, hit the cart, hit the wall, and it bounced back.
Yeah.
Okay?
That was fun.
And you were like, hey, remember this for later?
Yeah, well, this is now later,
Dang it.
Later is now.
Now
okay? So,
Now
let's
and again.
say here's this cart, and
Nice
it's
card.
got the plunger, and it has a mass of 0.3 kilograms, and it's moving with a velocity of
I don't imagine.
2.5 meters per second. Okay? So, if that's the story, and it's going to run into a wall over here, at this point, what's the only type of energy that it has?
Kinetic.
Kinetic energy, right? Now,
Translational.
when it hits the wall, what's going to happen to that kinetic energy?
Be transferred into spring potential energy.
It's going to change into us, right? Okay? So when this spring is fully compressed, how much us is it going to have relative to the amount of kinetic energy that it had before?
Same.
Same.
Yes.
So, if you think about it, a spring,
How much?
which if you, it takes a little bit of a faith, but if you think about it, a spring is like horizontal gravity, okay? So, if I throw this up with kinetic energy, it changes into,
Potential.
Oh.
Kinetic. Yeah.
right? So if I push it and it hits a wall, it turns into
Us.
us.
S for sideways.
Yes. So that's, ooh, nice.
Sideways.
So that's why I said you can think of a spring as being, in this case, horizontal gravity. So, here's what we're gonna do.
Because it's gravity.
Again, if you set up a chart or not, that's up to you. But again, if your answers are wrong, I'm not grading it.
I hate a chart.
So in this
one
situation, we
chart.
can have KT, we can have us, and we can have the sum. Now, it's possible, which you will see eventually, that I could have the cart up on a ramp
Oh no.
as UG, it would roll down, change into
Kinetic.
kinetic, and then the spring would get compressed, and then it would change into
Us.
us. So it's very possible you might have three types of energy all in the same problem.
Fun.
Now, so this is just like throwing the ball up in the air. What's the only type of energy that it has as it rolls?
As it rolls, it has kinetic energy.
That's it. True?
True.
Nothing else. So, the kinetic energy
Heat energy.
is going to be one. So somebody take 0.3 times 2.5 squared and then take half of that.
That square, half of that square.
So 2.5 squared basically times 0.15.
0.938.
What?
So call it 0.94.
Wait, what? 2.5 squared times 0.3 and then divide that by 2.
Times 0.
He's wearing a Bronco shirt. You got to give him time. Okay.
I
Even your
said-
pencils.
Now, how much us do I have?
Duh.
0.
OJ, right? Because it's all kinetic. True?
True, sure. What do you say, boss?
So that's 0.94 joules. Now, here's what I want to begin to look at. So the spring constant is on this is 3.00 times 10 to the third newtons per meter, which is pretty big, okay, because pretty stiff spring to stop this thing. So when the spring is compressed 1 centimeter, it's about like yay. What I want to know is how fast is the cart going? Okay? So, since you know how far it's been compressed, I mean this far, what can you find at that point?
The spring energy.
Yeah, so that would be the same idea as me throwing this up in the air and saying, oh, hey, it's gone up to a height of a half a meter. How much UG does it have? How much kinetic energy is it still going to have? So, it's the same idea. So, instead of having an UG and KT container, we're going to have an US and a KT container. So this kinetic energy container was filled up to 0.94 joules. And we're going to transfer some of that KT into US. So here's the drill. So you know that since it's how far it's been going to be compressed, so we can go US equals 1/2 kx squared, which is going to be 1/2 times 3.00 times 10 to the third newtons per meter times 1 centimeter converted into meters is 0.10 meters squared. Now, obviously, what does your answer have to be less than?
0.94.
Yeah, if you do this calculation and you get an answer bigger than 0.94, something has gone horribly wrong. Because you have created energy. So do the math, take 0.01 squared times a half times basically 3,000.
Equals a number. Plot twist, the well just
1.15?
adds energy.
What'd you
to the
get?
system.
0.15.
Okay,
Sorry,
That's right.
so I've got 0.15 joules of us. Okay? So is the cart still moving?
Joules of us.
Cohen?
Is the cart still moving?
Yes.
Sure.
Why?
Because, no. Because it doesn't have kinetic. It just has,
It's still moving. It hasn't gotten all of the distance, right?
oh, yeah.
Because how much kinetic energy do I have?
Less than.
Less than 0.94.
0.94,
But
right?
it's more than 0. Yeah.
Yeah, because
More than
your joules would
0.15.
be 0.94 if it had compressed fluid.
Because
Yeah.
the sum total still has to add up to
0.94. Yeah.
0.94 joules.
Mhm.
True?
True.
True?
True.
So if I
Very
take
true.
0.94 minus 0.15, I get
0.79
0.79 joules of.
Kinetic energy.
kinetic energy.
So how can I use that to find the velocity?
use,
Well, 1/2 MV
1/2
squared.
MV squared.
Yeah, I know kinetic energy equals 1/2 mv squared. So we do the 2k over m, the square root of that, I get my velocity. So if somebody take 2 times 0.74 joules and divide that by the mass of, what was the mass of this thing? 0.34. Now, obviously, what does your answer have to be less than?
The
0.94.
initial- No, the initial 2.5.
Which was 2.5, right? So if you do this and you get an answer bigger than 2.5, you have done something horribly wrong, or bad if you're Cohen.
It hits the wall and accelerates.
28
Well, it does accelerate
Well,
when it hits
more.
the wall.
I feel
It
bad.
accelerates to the faster,
Yes.
not to the slower.
I feel bad for
accelerates
people who have to watch
faster.
this in fourth
So,
grade.
do the math, what do you get?
The number's sure, certainly.
Oh, good.
Cause like, what if I know
It's
that I know
actually
that that's
imaginary.
what I'm
You
It's
get
better-
imaginary energy.
Yeah.
I.
That's what it feels like when I wake up in the morning.
I have energy.
2.23.
That's an old calculator, could be wrong.
I might have plugged that in wrong because
I
this is
think
not
you
the
might have.
this is not the calculator I normally use. So
It's literally the
Jeez,
exact
Tom.
same though. Like it.
no, it's not.
It has. Do you use it at 84 plus C, right?
Yeah,
It's
but it doesn't have the
literally the exact
fractions stuff.
Holy, just do the
Okay, well,
calculation.
okay. Doing it.
Oh,
now.
I accidentally put a
I got
5 on the end of that. One sec.
2.2. 2.
Oh.
Oh, that's what I got.
Yeah, that's what I got.
As opposed to 2.23. Sorry, my
Yeah,
bad.
yeah, that is your bad.
Really?
2.2.
Okay, 2.23?
2.22. 2.22.
Okay. Does that answer make sense?
Yeah,
Why?
it's less than the
Less
initial
than
velocity.
2.5.
Less than what you started
It didn't-
with, right?
So it's distance squared, so you'd think that like it would.
Now, here's the last thing we need to figure out,
Yeah,
is how far can the spring collapse?
nobody knows.
Until it stops.
Well,
Maximum compression.
What would be, now, what is maximum compression? How much kinetic energy are you gonna have?
0.94.
Huh?
The same as the.
How
Zero,
much
zero,
kinetic
zero.
energy are you going to have
0.
when this thing is completely compressed?
Zilch.
Zero.
Like grade
Goose
point
egg.
Okay? Zero. Because when it's fully compressed, it stopped to change direction, right? So, if you go back up here,
He's pretty much right.
when it's fully compressed, how much us are you gonna have?
All the
Will.
way to
Married
us.
to his studies.
0.94.
0.94 joules. How much kinetic energy are you gonna have?
0.
So no.
Goose egg, right?
Just
Academic integrity.
So, 0.94 joules,
Sherry's kidding.
which is your us, let's talk about us,
Force times distance. I don't know.
equals,
Shut up, Cohen.
1/2
I
K
agree.
distance squared.
so,
Stop being
I
bad
need to
and
get
bad.
x by itself. Danny Wynn, what am I gonna do?
1, 2.
You know what?
Give me a second. I have to think about this.
I hate fractions.
Times it by 2.
To us,
Yes. And divide by your distance squared.
I wanna get
We're
distance.
solving for distance,
Oh,
Danny.
never mind. Divide by your Newton meters
And,
and square root of that.
That distance doesn't make sense.
it's gonna equal x. Now, what does your answer have to be greater than?
1, 0, greater than 0.
Danny McGuy.
Obviously, it has to be greater than 0, but in terms of the context of the
observation,
problem,
Great
what does it have to be
observation,
greater
Cohen.
than?
It's just 18.
0.01? Because if it was 0.01, 1 centimeter, it was still moving, right?
Oh yeah.
Ah.
What's our K?
3,000. So 2
3,000.
times 0.94 joules divided by 3.00 times 10 to the third newtons per meter.
I wasn't sure what you want. I got 0.025.
Okay? 2.5, about like it. Okay? Now, what would happen if this spring had a smaller spring constant?
It would compress more
Yeah, why?
because you're dividing by a smaller number.
Yes,
so
mathematically, you're dividing
They go
by
big.
a smaller number. Okay,
it's easier to
So,
it's easier to compress
as
the
you
spring,
go
so it
through
compresses
these-
more.
okay? Again, charts
Sometimes physics is like
are optional. It's up to you. But if I don't see them and your answer is wrong, if you look at my, let me put it this way, if you look at my answer keys, how I work them out, I've got charts. So,
Seems like it would just be harder to not do it.
I have one chart of the.
alright, stop y'all the camera.
I have one
I
chart.
looked at the.
Well, like we only needed it